Welcome to Linear Systems EEE582, Module 1. And today we are going to continue the linear algebra review. And we will study linear maps and their properties. In this first part of the lecture, we will work with the adjoints of linear maps and their meaning to different applications. And in the later sections, we will look at projections and singular value decompositions. Linear maps have a very standard definition. They are maps from a vector space to a vector space, which obey the superposition principle. So, the transformation of a linear combination of two elements in a vector space is the linear combination of the transformations. This is a very standard definition, and a pictorial representation of that is the linear map A, which takes elements from the vector space X and maps them to a vector space Y. I like this representation where X and Y are given as some coordinate systems of the plane, and this is a much better representation rather than using generic sets where X maps to Y. Now, linear maps have a lot of interesting properties and several definitions that are associated with them. Some important sets that are related to linear maps is the null space of A. And by definition, the null space is all the x's in the domain such that AX is 0. So all the x's in the domain that map to the origin of the codomain. This is always a subspace of X, of the domain. The range, on the other side, is all the y's in the codomain. In general, the codomain is bigger than the range, and that's why we use this terminology, such that there exists some x in the domain for which AX is equal to Y. This is a subset of Y, of the codomain. And it's not always a subspace in the sense that it may not contain all its limit points, but for finite dimensional codomains, the range is a subspace. Again, all of these rather esoteric definitions, they do have a lot of importance when we try to form optimization problems and solve them using, in particular, recursive algorithms or sequential algorithms. And we are asking for the limit points and whether they converge to a minimum or not. Last one of the definitions here, what is the rank of the transformation A? And this is defined as the dimension of the range of A. Now, another important object that's related to linear maps is the adjoint of the linear map. If we have a transformation that maps x to y, and here to make it a little bit more interesting, I added another dimension on the range, on the codomain space y. The adjoint map is, again, a linear map which takes elements of y back to x. It's not an inverse, but it's a transformation that has a certain particular property, which is defined here through the inner product. So the adjoint is defined as the map which produces the same inner product in the space y when we take the inner product of an arbitrary element with ax, and then taking the inner product of the adjoint map operating on y with the element x. The map that satisfies, the map A star that satisfies this property is the map that we call the adjoint. In the sense of matrices, we know this as the transpose or the complex conjugate transpose of the matrix. For my particular example here, the map A takes R2, which is my X space that I have defined here, has dimension 2 coordinates, and maps it to elements in R3, so it does produce a three-dimensional element at the end. Now, the adjoint is simply the map 1, 2, 3, 1, 1, 1, which maps R3 to R2. It's not an inverse, it's just a map that goes backwards, and it has this very important property regarding the inner product with the elements of the space. It's time to do some derivations and see how something like this can work out. I take the inner product of y with ax. Y is an element in the codomain, and x is an arbitrary element in the domain. Using the definition of the inner product as as y transpose x. This is the standard definition in the Rn spaces that we have seen so far. So the inner product here in the codomain, which is R3, is going to be Ax transpose y. Now I'm going to use properties of matrices and vector multiplications. I will break up this product. This is X transpose A transpose Y. And I will regroup the later part. So X transpose of A transpose Y. But now this one is an inner product in R2, according to my definition. So this is the inner product of A transpose Y with X. And it's an inner product in R2, not to be confused with the inner product in R3. There are two different objects, even though we write the same formula for them. Now, we can draw some quick conclusions. If we're mapping Rn to Rm, like so, then the adjoint of a linear transformation is simply given by the transpose of the matrix. If we're working with complex valued elements, then the adjoint is the complex conjugate transpose, which also has a fairly standard notation Hermitian A with a superscript H. Now to draw a little bit of a distinction between inner products and domains and inner products and codomains, I will look at a slightly different map, a more interesting map in the context of linear systems, that which is an integration with a kernel like it's given here. The kernel of integration is e to the ATB, and we haven't talked about what is a matrix exponential, but you can still take it as an expression, as a function of time. You can think of A being scalar for the time being. It doesn't make, you don't lose much of the significance of the problem. So this is an integral transformation, and what this integral transformation does, it takes functions. So the input u is a function which is in L2. I have to assume that it belongs to a certain space, and L2, the space of energy functions, is good enough right now. And it maps these functions into elements of Rn. So what comes out of the integral is an element in Rn. If A and B are scalars, then it's just real numbers, R1. I will do a few calculations here to show that the adjoint of this linear map, it's quite obvious to see that it's linear, it satisfies the superposition principle for different elements of L2 for different functions u. So the adjoint is a multiplier. And this multiplier takes elements from Rn, x's in other words, and maps them into time functions. Okay, so let's do a little bit of work in terms of the calculations. I'm going to take the inner product between a vector x, which is in Rn, with the image of this map with an input u. And this is an inner product which is in Rn. Just as a distinction, A here is going to be a matrix in the e to the at, but the boldface A is what I denote as the map, the linear map which we are interested in, to different objects. I will try to make a good impression of a boldface when I write the expressions down. So now this is, according to the inner product in Rn, this is going to be the vector AU transpose x. Now AU is the integral operation, so I'm going to write as an integral e to the a tau bu of tau d tau, and take the transpose of that, multiplying x. Now the transpose distributes inside the integral, so I'm going to have integral u transpose of tau, if it's multidimensional, b transpose e to the a transpose tau d tau, and then we're also going to have the x inside the integral, so I better stick it before the d taus. Now I'll go to the next line. Recalling the inner product in L2, I can separate the two elements of the inner product here with different groups. I can look at U of tau transpose as one group, and then the rest of it is the element that comes from L2, so that's going to be the part of the adjoint. So this will be the inner product of the first one with the transpose will be the second part of my inner product in L2, and the first part will be whatever we have in the second grouping. So B transpose e to the A transpose tau x. And this is what I want to define as the adjoint map operating on X, inner product with U, and this is an inner product in L2. So A star operating on X, the adjoint, is B transpose e to the A transpose tau x, and it's a multiply by this function B transpose A to the A transpose tau. Now this is in L2. For stable matrices A that have eigenvalues in the left half plane, but that is rather a detail at this point. It's a technical issue. We don't have to worry about it right now for the development that we do. The converse is also true. The adjoint of a multiplier is an integral transformation. Now this is a rather interesting example because it is the cornerstone of the development of linear systems in relation to the theory that has to do with controllability and observability of linear systems. How we can design controls that achieve a certain objective and how we can observe the system internal states by looking at the outputs, or in other words, limited information that comes out of the systems. So we look at linear maps A and their adjoints. And one of the very important observations here is that when we have these two objects, these two transformations, there is a certain fundamental decomposition, a geometry that gets inherited by the domain and the codomain in the way these maps operate. So we start with a linear map A, and I'm going to assume later on that I'm going to make use of its adjoint as well. But when I look at this linear map, I have a domain X and a codomain Y, and I know that I can decompose them in direct sums. The first direct sum, in the decomposition of the domain, I'm looking at the subspace, which is the null of A. Null of A is an important subspace, which is all the elements that get mapped to 0. So in other words, they go through the linear map and don't produce any output. And whatever is left is the orthogonal complement of that. Similarly, I can look at the codomain, Y, as the direct sum of two subspaces. One is the range of A, and the other one is what's left. What's left in the sense of orthogonal complements. Okay, technical detail once more. The formula, this decomposition is true if the range of A is itself a subspace. In general, this will be the orthogonal complement of the orthogonal complement of the range of A, which is the smallest subspace that contains range of A. But other than this technical detail, the general decomposition is quite intuitive. Now, in terms of our newly found knowledge of adjoint transformation, the following relationships hold in terms of these four fundamental subspaces. The null of the adjoint is the orthogonal complement of the range of the linear map, and the range of the adjoint is the orthogonal complement of the null. So if you want as a mnemonic, you switch null and range and switch adjoints and perps. I'll get to the picture in just a minute, but let me write here more precisely what the linear map and its adjoint, these two operators, what they map in terms of sets. So the linear map A maps the orthogonal complement of the null to the range. Everything else in the domain maps to 0, so it's not of very much interest. Everything else in the codomain doesn't have a pre-image. On the other side, on the adjoint side, the adjoint takes the range of A according to this relationship of the four fundamental subspaces to the orthogonal complement of the null. This is not an inverse. So in other words, A takes you from the orthogonal complement of the null of A to the range, and then A star gets you back from the range to the orthogonal complement of the null. That's not an inverse operation, it's just the way the maps work. What's important is that this map is one-to-one. So the overall map can be invertible, And a lot of the results and a lot of the theories that we'll develop will rely on maps like this, doing operations like that. So let's look at the picture and what A and A star will do. So here's the map A, takes my R2 two-dimensional space, which is fine for the purposes of visualization, into R3, and it has a null space. Let's say the null space is this, the blue line. So everything from the blue line, it will go to the origin. And let's say the green line here is the range of A. So all the elements that we map under this transformation will map on the green line. Everything else is unattainable. Now, the adjoint transformation will take R3 back to R2, this is the orthogonal complement of the null of A, and the orthogonal complement of the null of A will be the range of the adjoint transformation. So everything that gets mapped from R3 will go back to this line. And in particular, it's the range of the transformation A that gets mapped to the orthogonal complement and back. A moves this way, and A star moves this way. The orthogonal complement of the null of A is the null of A star, of the adjoint. So all of this red will map to the origin. That's in terms of orthogonal complements, direct sums of different vector spaces. Any other space, any other element in X or Y gets mapped according to its coordinates. We analyze the elements of the linear vector spaces into their canonical coordinates, and each one maps according to the linearity property and superposition. So very important relationships here. These are some equalities in terms of sets, which are interesting to derive. The derivation is, in some cases, easy, and in certain statements take a little bit more work. But fundamentally, we follow a very standard procedure. We take an element in null of A star, and we show that this element belongs to the orthogonal complement of the range of A, so it's orthogonal to the range of A, and vice versa. We take an element in which is orthogonal to the range of A and show that this is also null of A star. It's a very standard derivation which exists at this point under the four fundamental subspaces for linear maps. So as an interlude, I'm going to define a couple of optimization problems and see what some interesting applications come out of this theory. We have two fundamental optimization problems that we want to solve in this context. One is a minimization of the difference between AX and a Y. So where these problems come up. We try to derive the best model approximation of observations. a line fit problem. Suppose we collect data. Down here we have time, and here we have measurements. So at different TIs, we collect measurement yi. So these are our observations, TIs and YIs. We want to find a straight line that does the best approximation of these measurements. So the straight line typically will be defined by an intercept and the slope. So what that means is that we create a model, yi is some coefficients. I'll give them the notation capital AI. And what capital AI is at this point is 1, constant, and the time. And X, which is, so this one corresponds to the time, and the X will be the coefficients of the equation, which are my unknowns, the variables that I want to optimize. Then I can define the optimization problem, the least squares optimization problem, as the minimization over X of the summation of yi's, which is the observations, minus AIX, which is the model estimates, the model outputs. So you take the sum of the squares and you try to minimize that over X. So this would be the least squares estimate if we solve this optimization problem. How to solve the optimization problem? We need a couple more lectures to develop the necessary background. Another way to look at the same problem is by concatenating the AIs into a big matrix, multiply with the X's, and subtract the vector of Y's. We want to minimize the norm of this difference. When I look at it from this perspective, Y here is the vector space that contains my Y's. AX is part of a subspace. It's whatever a subspace of Y contains. So all the AX's will be a subspace of the big space Y. So this is also the range of the transformation A. And now Y does not have to belong to this subspace, but it's a vector of elements. It can be arbitrary, it can contain noise, it can contain things that are not modelable by this simple linear model that I have. So Y is an element of this space. We want to find the best approximation of this Y with an element on the subspace AX. I'm not going to solve this problem now, but I will set up the tools to do that later. A dual of that problem, a dual in a certain sense, is the other side of the fundamental minimization problems. Minimize the norm of a vector x such that this constraint ax equals b holds. Now, this finds applications in minimum energy problems, and I will define the problem, a simplified version of this problem here. So let's suppose that we have a system where the output is defined as a convolution model in terms of the input, and H is the impulse response. So let's say we have measurements, Y from Y as the output, and let's suppose that Y0 starts from 0 as an initial condition. Then UI, I going from 0 to n minus 1, are the different controls that we can apply to the system. The HKs are the impulse responses, the impulse response coefficients. So how the system weighs past inputs. And N here is going to be the horizon of the problem. So for how long we need to look at this system. So the X, which is the quantity, the control, which I want to optimize, is defined as all the possible inputs that I have, U0, U1, Un minus 1. And my linear map, looking at this convolution model for the output, will be the coefficients of the impulse response, n minus 1, etc., h0. Just to make the example slightly more concrete, although not necessarily representing any particular system. So let's say our system simply averages the last three controls. You can use, let's say, systems that are defined by differential equations and set up the corresponding impulse responses, but these will be problems that will end up with some infinite dimensional components. We will need to develop the theory before we are able to write down the correct equations for that. So this finite averaging model is good enough to visualize the problem. So what I want to do with a problem like this is now minimize the energy of X, the energy of my controls, subject to the condition. I'm starting with initial condition 0. And I end up with the output 1. So, well, then minus 1 here. So my condition is AX equals B with these particular values. Pictorially, what that means I'm going to map X into the codomain here, which is the values, the final values of the output. I want to go to a particular location as far as the output is concerned. And I have a lot of different options. And these options are determined by the map AX equals B. The set of all the x's which satisfy this equation is a variety in the domain. So my big space here is the domain, which is all the values that the x's will take, the vector x, so that the n values of the input. AX equals B is the subspace that gives me my constraint. And I want to find the minimum energy input. So in other words, I want to find the X minimum norm, which is the closest to the origin. I will pause here for a minute and continue with this development in the next lecture. Thank you for your attention.